Yesterday we looked at the general form of a quadratic function, so f of x equals ax squared plus bx plus c. There's also what's called the vertex form of a quadratic function, which is here, and this you actually saw in chapter 2. So if it looks familiar at all, hopefully it does because you just saw it this year in chapter 2. But the a times the quantity x minus h squared plus k, we had talked about that in terms of transformations in chapter 2. The reason it's called vertex form is because when you look at this equation, the ordered pair hk is the vertex of the parabola. So you can just look at the equation itself and know right away what the vertex is versus what we did yesterday. With this form, you have to go through a couple calculations to find the vertex. So eventually, later in chapter 4, we're going to be looking at how do we go from the general form to the vertex form. How do we rewrite it into this form? We're not doing that today. We will later on. So what I wanted to remind everybody of is these values, A, H, and K. I'm just going to grab a couple of highlighters here. They all perform some sort of transformation on the parent graph. The parent graph for a quadratic function is just f of x equals x squared. So x squared is the simplest quadratic function there is. And that is a quadratic function or a parabola that has a vertex of 0, 0. Okay, so that's the parent graph. So A, H, and K, those three values all perform some sort of transformation on that parent graph. All quadratic functions stem or are transformed from this. So I do have that vertex form. I typed it into Desmos. I'm going to show you something Desmos can do if you're not familiar with it. I typed it into Desmos so that we can look again at how these different values change the graph. We're first going to look at K. So how does K transform the graph? So if you want to look up here, because I'll show it on Desmos. I have it right here. So all I typed in just the formula. I have this zoomed in so you can't fully see it. I typed in the formula, and when you do that in Desmos, what happens is anytime you have a variable written in, like the A, H, and K, it asks you if you want to make a slider so that I can just press, for example, K. The parent function has a K value of 0. So if I change K, so I can just press play here, it'll show you on that graph what happens when K changes. So it shows you how K is changing it. It's kind of going in and out of the graph there. So what's happening to the graph? What effect does K have? It's moving it up or down. So it does look like the shape is changing a little bit, but that's only because like as it moves down, you see more of the graph. So it's not really getting wider. It just looks like it is. But K moves the graph up or down. So I'm going to change this back to 0. So on your sheets here, the transformation K does, it's called a vertical translation. A vertical translation. So I'm going to add to that. It shifts it up if K is positive. So if K is greater than 0, it shifts it down if K is less than 0 or K is negative. So it's a vertical translation, shifts it up if K is positive, down if K is negative. And then next we'll look at H. So now again, if I go back to Desmos, I'll come back to the screen if you still need to write something down so you'll be able to see it. So again, in the parent function, the H is 0. So if H is anything else, it's a transformation. So if I play H, you can see what happens to the parabola as H changes. So what would you say H does to the graph? horizontal translation. And then notice, so where I stopped it, notice if h is negative, it's going to move it to the left, and then if h is a positive value, it'll shift it to the right. Hunter, I'll write you a pass. Yep. All right, so going back to here, so h is a horizontal translation. So it moves it to the right if h is positive, so greater than 0. It moves it to the left if h is negative or less than 0. I do want to show you, though, one additional thing with the h, what it would look like in the formula, because in the formula it's x minus h. So what I want you to realize is, as an example, if h is, say, positive 1, then in your formula, I'm just going to write this parentheses squared, just this part. What you're going to see is x minus positive 1 squared. So when you look at an equation, if you see x minus 1, you might want to say h is negative 1. That really means h is positive 1 because of the minus in the formula. But if h is negative, say h is negative 1, if I substitute a negative 1 in for h, I'm going to have x minus a negative 1, which is really plus 1. So it's going to look like x plus 1 quantity squared. So when you look at an equation, like even look at example 1, there's x minus 5 quantity squared. So what is h? Positive 5. So here h is really positive 5. H is always the opposite sign of what it looks like in the equation. And it's because the formula has a minus here. So make sure you understand that so you get the transformations correct. All right, and the last one is looking at how A transforms the graph. So the A value multiplied in front. Well, I'll play it and then we'll talk about it. I do want to say this A here and this A, they're the same A. So I know this formula has ABC, this formula has AHK, but the A's are the same. Like they're the same number in both forms. They do the same transformations to the graph. So when we go from one form to the other, they are the same value. That will help you when we get to that point. So I'm going to change h back to 0. So the a value in the parent function, a is just 1. If you think of y equals x squared, the value in front of x squared is just 1. So if a is anything besides positive 1, a transformation is happening. So I'll play a. So a actually does a couple of things. So what is one thing you'd say that a changes? Yep, there's a compression / stretch. So one thing that happens is as your a value, like here a is 2.16 as I stopped it, so as a gets bigger, if a is bigger than 1, notice the graph gets narrower. That's described as a vertical stretch. It's like you're taking the two ends of the graph and pulling them up, which makes it skinnier. So I'm going to write this way, though, that if the absolute value of a is greater than 1, because something else happens if a is negative. So I need to go back to my screen, though. If the absolute value of a is greater than 1, this creates a vertical stretch, which makes the graph appear narrower or skinnier, if you wanted to add that in so you know what that means. And then if a is a fraction between 0 and 1, so say it's 1/3 or 2/5 or 7/8, so something that's less than 1 but still positive, so still greater than 0. So So if I'm going to put the absolute value of A is between 0 and 1, so it's a fraction, this would be a vertical compression, which is going to make the graph appear wider. It's like you're pushing down on the two ends, so it looks fatter. And I'll actually show that. Something else happens then if A is negative. So if A just in general is less than 0, it's actually a different transformation. So I'm going to go back. I'll come back to this screen if you need to write something down. But I do want to show here, here's an example of like A is 0.2, 0.3, so it's wider. It gets wider if it's a decimal or a fraction between 0 and 1. Once I get to a negative A value, though, what happened? If A turns negative, what would you say is happening? It's a reflection, yes. Now, the reason I had the absolute value bars written in is notice if it's a negative number that's still a fraction or a decimal that's smaller than 1, it's still wide. Once I get to like -2, -3, -10, it still gets skinnier, so that's why the absolute value is there. So the negative, if A is negative, this is a reflection over the x-axis, which what that means is your graph is going to open down. We actually talked about that yesterday with our general form. We said if A is positive, the graph opens up. If A is negative, the graph opens down. Same thing here. The function itself just looks different. Okay, so what we're going to do with this today is I want to go through with you. I'm going to go through a couple examples, and then there's 3 on the back that I think I'll have you work on. And if you don't finish them in class, you can look at them outside of class also just to get some practice with it. I'm going to show you how to graph if you're in vertex form versus how we graphed yesterday in the general form. But I also have space below each of the examples. I have blanks for you to list what transformations have happened based on your A, H, and K values from up here. And the number of blanks that I have are the number of transformations that are happening. So if we look at example 1, because we're still going to graph these by plotting specific points, we're just going to then talk about the transformations. And we are going to be using transformations tomorrow. So I'll kind of show you tomorrow how this leads in. So we already said, for example 1, this is graph and describe the transformations. We already have H. I'm going to list what the A value is and what the K value is also. So just like yesterday, how we found A, B, and C right away, here we can find A, H, and K right away. What is the A value for this function in example 1? A value is 1, yeah. So if A is 1, that means there is no transformation happening for A. There's no reflection, there's no vertical stretch or compression, because A is 1 in the parent graph as well. We already said H is 5, so transformation is happening there. K is what? 3. So there's a transformation happening there. So we'll get to that part. So when I graph HK, that is your vertex. So I already know my vertex is the ordered pair 5, 3. And I can plot that right away. Now yesterday we drew in the axis of symmetry and then we plotted the vertex. So here I can, once I plot the vertex, I can draw a vertical dashed line through it because that will be my axis of symmetry. So you can still draw that in. It's just here it's easy to find the vertex right away. And then actually making the table, like writing it down, that's up to you, just like it was yesterday. So I'm just going to put my vertex in the middle of a table. But then what I need to do to finish graphing this is just I need to substitute in a couple of x values on either side, and then I can reflect them over. So again, I get 5 points total. So for example, I tend to substitute in values that when I plug them in for x, it makes what's in the parentheses positive, just because it's easier to work with, but you can plug in whatever you'd like. So I would probably, looking at this, I would plug in 6 for x. Did you say y? I would plug in 6. I tend to stay close So if I plug in 6, I'd have y equals the quantity 6 minus 5 squared plus 3, and then you just use order of operations to evaluate that. So I know 6 minus 5 is positive 1. Positive 1 squared is still 1, and then 1 plus 3 is 4. So this is 4. So I have 6, 4 on my graph. And then I can reflect that over to what point? 4, 4 is also on the graph. So I plug in one x value and I really get 2 different points out of it. And then I just need to do that one more time. So again, I tend to stay close, so I'd probably plug in 7 and reflect it over. So I'd have y equals the quantity 7 minus 5 squared plus 3. So 7 minus 5 is 2. 2 squared is 4. 4 plus 3 is 7. So I can plot 7, 7, and that reflects over to what? What other point? 3, 7. Okay, once you have 5 points, draw in the parabola. And then list the transformation. So the graph can even help you when you're describing the transformations, but again, it's getting you familiar with the idea that this graph is just transformed from the parent graph somehow, which is this graph up here that just has a vertex of 0, 0. So if the h value is positive 5, what transformation happens if the h value is positive 5? It went to the right 5. So I can say translated right 5, or if you said shifted right 5 or moved right 5, that's fine. That's fine. Translated is probably the most mathematical term to use, but if you said shifted or moved, that's fine. And then if k is positive 3, what happened? It went up 3. So translated up 3. Okay, and you can see that from the graph. The vertex started at 0, 0. It went over 5 to the right and then up 3, and that's where your new vertex is. So that should make sense when you look at the graph that those transformations happened. The idea behind this and how we're going to use this tomorrow is if I give you, or if you're given an equation or you're given a graph and you want the graph to move somewhere else, you need to know which of these 3 values you need to change and how you need to change it to get it to move where you want it. So if you want something to move to the right, you know you're going to be changing the h value. If you want something to change so that it's now opening down, you know you're changing the a value. So that's where we're getting with this. Let's also look at number 2 together. Just go through one more and then I'll have you do the 3 that are on the back. So this is graphing y equals negative, or the opposite of the quantity x plus 3 squared, and describe the transformations, which I have down here. There's 2 of them. So for this function, what's the a value? Negative 1. What is h? Negative 3. What is k? 0. Yep. So the a changed because it changed from positive 1, now it's negative. The h changed. K, there's no change here because in the parent function k is 0. So that's why there's 2 transformations from h and k, or h and a, sorry. So I know my vertex is hk, so negative 3, 0. And then I can also dash in the axis of symmetry, bless you, through the vertex. I'm going to make a table, but again, writing the table, that's up to you. So now I just substitute in a point on either side, reflect it over. I'll let somebody just pick an x value to plug in. Negative 4. So then y is equal to, I'm going to actually write the negative that's in front, I'm going to write it as negative 1 in front of the parentheses. So negative 1 times negative 4 plus 3 quantity squared. So again, be careful with your order of operations. So I have to do in the parentheses first with the exponent. So I have negative 1 times negative 4 plus 3 is negative 1, and negative 1 squared is positive 1. So I end up getting negative 1 times 1, which is negative 1. So I have negative 4, negative 1. That reflects over to what other point? Negative 2, negative 1. And then I just need one other point to plug, or one other x value to plug in. Negative 5. So y equals negative 1 times negative 5 plus 3 quantity squared. So in the parentheses, negative 5 plus 3 is negative 2, and negative 2 squared is positive 4. So I end up getting negative 1 times 4, which is negative 4. And if I reflect that over, what other point do I know? Negative 1, negative 4. Okay, so what is one transformation that took place? It was reflected over the x-axis. And yep, I heard somebody else say too, it's translated to the left 3. So have an idea of what transformation should be happening when you find your A, H, and K values. The graph that you can really make sure, if you're saying, oh, A is negative, it should open down, and then you graph it and it's opening up, you know you graphed it incorrectly. So having that idea of what it should look like is, well, should be helpful. Hopefully will help you. So what I'd like you to use the remaining time for, there's 3 problems on the back. I'd like you to work on those, finish them, whatever ones, if you don't finish all 3 before you leave today, finish them for tomorrow. We'll correct them, and then we have an activity for tomorrow. But there's no additional assignment other than the 3 practice ones that are on the back of this sheet. And I'll walk around. I can check what you have because I have the key. I can answer questions you have. Just let me know if you have questions.